All right, we are live, everyone. Good afternoon, NOVA fans, and happy Tuesday. My name is Gina Veramo, and I'm the Outreach Manager for NOVA. And I am thrilled to be joining you today for the third and final virtual field trip event in our NOVA Universe Revealed series. So during this series, we learned how to observe variable stars, and we got a sneak peek at the James Webb Space Telescope just a few days before it launched. And today we're wrapping up our series with one of life's biggest questions, the existence of life on planets other than Earth. So far, telescopes like Kepler have identified and confirmed more than 4,000 exoplanets, and that's an incredible amount of opportunities to look for life. But will we be able to recognize life if we found it? So today I am honored to welcome our special guest, Dr. Clara Sousa-Silva, quantum astrochemist at the Center for Astrophysics, Harvard and Smithsonian, who's dedicated her research to answering this question. She investigates how molecules interact with light so that they can be detected on faraway worlds. She spends most of her time studying molecules that can produce life so that one day she can detect an alien biosphere. Her favorite molecule biosignature is phosphine, which I'm sure we will talk about today, a terrifying gas associated with mostly unpleasant life. When she's not deciphering exoplanet atmospheres, she works hard to persuade the next generation of scientists, many of you watching today, to become an active part of the astronomical community. If you've played the NOVA Exoplanet Lab, you may have also seen her have a special guest appearance as well. So throughout our time together, if you have any questions for her, please feel free to drop them in the Q&A section of Zoom webinar, or if you are watching us on Facebook or YouTube, you can put them in the comments and we'll try to get to as many as possible. So without further ado, Clara, I'm going to pass it off to you.
Well, thank you. All of that is true. Thank you for the lovely introduction, Gina. And thank you all for being here this afternoon. So as Gina told you, my goal is to identify one day life beyond Earth, no matter how weird that life might be. And today I'm going to tell you how I try to do it. And to do that, I usually like to reverse the problem. So could an alien colleague of mine, an alien astronomer who was looking for an inhabited planet in their night sky, find us? Could they know that we're here? So imagine, an alien astronomer is on the other side of the galaxy looking for a habitable planet in their night sky, and they point their telescopes towards our solar system. If they did that, and they point to their powerful telescope, but not necessarily any more powerful than the ones we've got, they would be able to split our sun's light into the sun's rainbow. And this is exactly what they would see. But they would see that our sun's rainbow isn't exactly perfect. You can see that some of the light from the sun would have been absorbed by atoms and even molecules in the cooler regions of the sun where they can survive, and leave behind these tiny little shadows, which we call absorption lines. And that's because molecules behave in a really unique way. Molecules still have to follow the laws of physics, like we do, but not quite the same physics that we are used to. And that's because molecules are so tiny that their physics have to follow the laws of the quantum world. And one of those rules is that they can only quantize very specific amounts of energy. And these specific amounts of energy correspond to specific wavelengths of light, which correspond to specific colors of the rainbow. Different stars have different atoms and molecules, and so they have different rainbows. And this one is just our sun's. So these alien astronomers could look at this image and using the universal knowledge of molecules that they got from their quantum astrochemists like me, and know exactly which molecules and atoms were causing these shadows, these absorption lines in the sun, and figure out its composition. But if they were patient, and also if they were really nicely aligned, they would notice that every 12 years, new lines would appear and then disappear. And then every 12 years appear again. And these lines we due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. So an alien civilization with really only slightly better technology than we have now would be able to study these new lines and know that Jupiter has this huge complex atmosphere with not just hydrogen and helium, but also methane and ammonia and hydrogen sulfide and many other gases. And if they were really, really, really careful, they may notice that every year, a few much fainter lines would appear and then disappear, and a year later appear again. And these, of course, would be due to the molecules in our own Earth's atmosphere, also absorbing new lines of the sun spectrum. So these alien astronomers could use this technique to try and get rainbows for all the solar system bodies. For example, here we see from the top, Venus, Mars, Jupiter, and the moon seen from Earth. And even from this really quite short distance, we're not far from these astronomical bodies, the light from these very different planets can appear really similar. But again, by splitting their light, we can see how different they truly are. And rainbows are really pretty, but they're really hard to work with. So instead, we use these lines you see here on the screen, which we call spectra. We just mentioned it earlier. And basically, it describes how intense light is at different colors, different wavelengths. So these alien astronomers could split the light of all the solar system planets and tell the difference between them by looking at their different spectra. And if they did that, they will learn that Venus is basically hell with very high levels of sulfuric acid. So any life there will really struggle, though we'll talk about that later. And Mars has a teensy tiny atmosphere, and they'll figure out it can barely shield its surface from radiation. So also not the most hospitable destination. But they would know that out of the solar system planets, there is something really special about the Earth, and that is we have a lot of life. So you can think of our atmosphere and its subsequent rainbow or spectra as a planet-sized message communicating to the galaxy that we have oceans and forests and huge ecosystems with rich life cycles, and also that we pollute an awful lot. And those alien astronomers would be able to know that on Earth, we don't just have an atmosphere, we have a biosphere, and we can do the same to them. So first, we do have to find the planets themselves, but we've been working on that for a really long time. We found Uranus in 1781, Neptune in 1846, Pluto in 1930, and then lost it again in 2006. Then we found our first exoplanet in the mid-90s and kept finding more and more. With Kepler, we found thousands of planets, and with TESS, thousands more. And with upcoming missions, we will find tens of thousands more. So we're getting really, really good at finding these planets, but we have only just begun finding atmospheres on these planets, and we still know very little about them. Future missions in space and on the ground will provide more information on these planets and their atmospheres, which means we are basically at the edge of being technologically able to detect the molecular signs of life. And that's what I do. Now, each molecule that could be associated with life, and we call those biosignatures, has a spectrum of its own, which look roughly like these that you see on the screen. And these lines describe how each molecule interacts with light, and that's how we detect them. Now, if we want to detect any of these molecules in an alien atmosphere, we do need to measure or calculate the spectra for each one of them. But this is really, really difficult, and there's very few people doing it, so I'm hoping some of you will want to join the force. It requires either lots of lab work, often in quite dangerous conditions, and a lot of computational work with supercomputers, which is what I do. And that can take many, many years of simulations. But if we do get spectrum and we use these spectra to detect these molecules in alien planets, on their own, they wouldn't necessarily indicate life. And that's because all of these molecules, all these biosignatures, have what we call false positives for life. And by that, I mean, they also have ways of being made that don't involve life, non-biological sources like volcanoes. And this is true for most of the molecules that life loves and produces. And you can see here, so on the left, in the first column, you have popular biosignatures on Earth that are produced by life. That's the second column, but also produced in other ways without life. And so this is a problem when we detect them. How do we know if we found life? You should know that this problem, a false positive problem, happens because these molecules are great, but chemically speaking, they're easy to make. So life makes them easily, but also not life makes them easily. So detecting any of these biosignatures by themselves on an alien planet wouldn't necessarily tell you found life. Now, there are two solutions to this problem, this false positive problem. One is to think about context. For example, oxygen on Earth is a biosignature, but on its own may not be a good biosignature. If, for example, our sun had different levels of radiation, or if our oceans were evaporating from a really intense greenhouse effect, or if the other gases in our atmosphere were different, then you could get large quantities of oxygen to accumulate in our atmosphere without any life interfering. But in the context of our sun and our planet and the rest of our atmosphere, oxygen is a really wonderful, robust biosignature. So the same is true for other molecules we usually consider in the search for life. These molecules, like methane and carbon dioxide, are only good biosignatures if we can attribute them to life after investigating the false positive scenarios. But that means understanding the atmospheric context, all the other molecules that could be surrounding them in an atmosphere that can explain whether it's life or not life, like volcanoes or oceans. But how many molecules do we need to detect on an atmosphere to play this game, to figure out if it is life or not life? Well, my old group at MIT tried to come up with a list of all the possible molecules that could contribute to the rainbow, the spectra of an alien atmosphere. And that list contains 16,367 molecules. So that's a lot of molecules for us to be able to study and detect in an alien atmosphere. So that's the first problem. But the second problem is we currently only have spectra for 4% of these molecules. So we're missing a lot of information. And that means our ability to understand the context of any biosignature we detect on an alien planet is not great. Which brings me to the other solution to the false positive problem. We can look instead for molecules that, although are less popular or less pleasant, but are biosignatures with low false positives. That means they need less context to signify life. A really good example here would be complex pollutants, so signs of industrial activity, which would be worrying for the alien planets because maybe they'll destroy themselves polluting too much, but it would be a clear sign of life. But that's a very extreme example. There's no reason to think aliens pollute like we do. So that's really an edge case. But there are other molecules that have low false positives for life. And my favorite of those is the phosphine molecule. Now, when I started working on the phosphine molecule, it was about a decade ago, and it wasn't considered a good biosignature. In fact, it was only known for two things. One, it was known for representing the violent storms of Jupiter and Saturn. It was detected in the upper layers of these planets, but it was a little surprising to find it there because on the top of Jupiter and Saturn, the pressure and the temperature are way too low for phosphine to be formed. But what happens on those planets is that phosphine is happily formed in the really intense, hellish depths of the planets, and then it's aggressively dragged up by violent storms, surviving to larger concentrations that we would have otherwise predicted. And that's how we find it. But on rocky planets like the Earth, we don't have these extreme environments like the depths of Jupiter. So phosphine is almost never made accidentally, spontaneously. Which brings me to the second thing phosphine is known for. On Earth, phosphine is mostly notorious for being a lethal and foul-smelling molecule. Phosphine interacts fatally with oxygen metabolism, which is what we use to live, and so it's a really effective killer. For this reason, we have, as a species, used phosphine as a pesticide in agriculture and industry. And sadly, for the same reason, we have used phosphine as a chemical weapon in wars, in the First World War, and really sadly, most recently by ISIS. So phosphine is mostly really awful and deadly and dangerous. But what I found was that it has one very important characteristic. For life that doesn't rely on oxygen, phosphine is perfectly safe. I confirmed this by reviewing all the reports of phosphine being detected all over the planet on Earth. And it's produced in lots of ecosystems that are low on oxygen. So places like sewage or rice fields or marshlands or the intestines of fish and the intestines of babies and actually the guts of almost every animal. Basically, life that doesn't need oxygen is very happy to produce phosphine. And these environments have life that doesn't need oxygen. So I thought, could I detect signs of a phosphine-rich biosphere on an alien planet without oxygen? To figure this out, myself and my team simulated lots of hypothetical planets on stars in our neighborhood in the galaxy to find out if we could detect phosphine on different types of planets. And we found that if we had a planet that had a hydrogen-rich atmosphere or a carbon dioxide-rich atmosphere around small stars, we could detect phosphine being produced by life. And if it was a planet orbiting a star like our sun, it would have to be a hydrogen-rich planet, so a puffy atmosphere of a hydrogen-rich planet. But we could detect phosphine, and if we did, it would be very interesting. And this makes phosphine very promising as a biosignature, specifically because what makes it really appealing is that if we find phosphine on a rocky, nice temperature planet, a planet that could have life, it seems to have no false positives for life. So definitely not a sign of life on Jupiter, but on a planet where aliens could live, it seems to be really, really difficult to make without life. To figure this out, we looked at just standard chemistry and we found nothing could really make it in any reasonable amounts. So then we thought, what about really extreme events? Maybe that planet has a lot of lightning or volcanism or a lot of meteors coming in. And here we found that even in the atmosphere types that would be best for producing phosphine, only a tiny amount of phosphorus, which is this atom here on top, could turn into phosphine, and never any amounts we could detect. So at that point, we looked into crazier and more implausible scenarios, and none told us that we could make phosphine on these planets. So that means that given our current understanding of potentially habitable planets, we now have this tweetable conclusion for our work that any detectable amounts of phosphine on a rocky planet cannot be explained without life. And when I submitted this work and tried to publish it in 2018, I thought it was a really cool conclusion, but it wasn't controversial. It was just me talking about a hypothetical, theoretical situation. I was imagining this distant planet, a tropical paradise with a complex biosphere without oxygen, producing loads of phosphine that we might one day be able to observe. Now, some of you might know that phosphine turned out to be a little more exciting than I had initially imagined, because a few months after I submitted this work, an astronomer in Wales, Jane Greaves, reached out to me asking for help with understanding a telescope observation, which you see here in white, and then 18 months later, a signal from another telescope, seen here in orange, that seemed to indicate that phosphine might be present in the clouds of Venus, the only potentially habitable location on Venus. Now, Jane knew this was strange, but she needed a phosphine expert to know how strange, and that's how our collaboration began. Now, the notion that phosphine, a molecule I had claimed was a really promising biosignature, would be present on Venus, the planet next door, is of course really exciting. And the press thought so too. But I want to say that before we jump on life as an explanation, there's still much about Venus we don't understand. And all we really know is that something weird is happening on Venus. And there is still plenty of controversy surrounding this potential discovery. And what we have to do now is figure out if the signal is definitely real. And if it is, it's definitely phosphine. And if it is, what or who is making it? And so to try to answer these questions, we are trying to look at Venus again with more telescopes that can help us answer those first two questions. And as we learn more about Venus, we can also make more better simulations of the clouds that can help us make sense of what's going on in there. But importantly, we also need more spectra for more molecules in the Venusian atmosphere that can help us figure out the false positives for any biosignatures we might confirm. But what I want to highlight right now is how a virtually unknown and really disgusting molecule became such an important piece of the puzzle in the search for life beyond Earth. And phosphine is just one molecule. Venus is just one planet. Even if it turns out that indeed we have found phosphine on Venus, this will not be the last time we find a potential biosignature on a planet beyond ours. So the question is, will we be better prepared to interpret such a discovery next time? That's what I spend most of my time working towards. But it's never going to be as simple as detecting a single interesting molecule on an alien planet. As much as I love phosphine, and I do, and as much as I love the more traditional biosignatures like water, which I do, the detection of life will not come from a single molecule. As the Venus story shows, the detection of life will be uncertain, and that uncertainty will only be reduced if we are ready to detect and understand more molecules. To find life, we'll need to consider the big picture, all the possible molecules that can together help us confirm that we've definitely detected life. But there are billions of stars, and orbiting them billions of planets, and in them thousands of molecules that we need to understand to be able to know what we found. And that is more stuff than we astronomers could ever do on our own. And I came to this realization a few years ago when I was writing my PhD. At the time, I was the head of education for the Twinkle space mission, which is a teeny UK satellite trying to understand alien planets. Now, I was doing this while I was also training as a high school teacher in a London school. And I will tell you, that was a really bad decision because turns out teaching is way harder than being an astrophysicist. But I tried. And while I was trying to teach as best as I could, I noticed that whenever my research into alien molecules was talked about in my classroom, the students and I would get into super interesting discussions. And that made me think, what if my students could help me understand these thousands of molecules on these billions of planets and stars? So I created a new program called Orbits, or Original Research by Young Twinkle Students, and recruited 15 of my own students to do research with me and 3 young scientists that agreed to help. And this is the first group of students, which we split into 3 groups, each studying the spectra of a molecule crucial for understanding alien planets. So this is Team Titanium Oxide, Team Acetylene, and Team Methane. These super cool kids learned astrophysics and quantum chemistry and programming, scientific writing, and they did original research on the 3 molecules. And they ended up going from being my high school students to being my official scientific collaborators. And they became co-authors on multiple articles. The students you see here then became mentors for the next year students and the next year after and so on. I hired someone to replace me when I left the UK, so the program continues without me. But since 2018, more than 100 school students have become published authors of scientific articles through Orbits. And to continue the sort of work in the US, I became the director for the Harvard-MIT Science Research Mentoring Program. I've actually just stepped down as director to focus on my research, but we still have an amazing team of dedicated scientists and experts running the program. And what we do is we recruit about 3 to 8 junior scientists as mentors, and then we help them adapt their current research to benefit from collaborating with high schoolers. And then we hire, train, and pay a salary to about 10 to 15 local high school students, assign them to mentors, and then they perform original research throughout the academic year. And at the end of the program, we have a symposium where the students present their research to the whole scientific community. So now we have a lot of young people working towards understanding alien planets, which is great, because ultimately it will not be the next generation of telescopes that will revolutionize astrophysics, but the next generation of scientists. And looking for life is an interdisciplinary science. We need astrophysicists, but we also need engineers and biochemists and quantum chemists. And when the time comes, we will need philosophers and poets and lawyers if we're ever going to make sense of it all. So the last thing I want to show you is what happens when you add musicians to this list. So this is the phosphine spectrum, which is actually what I spent my entire PhD simulating. And I know it looks simple, but it's actually composed of the collective force of 16.8 billion tiny spectral features, those absorption lines. And I've calculated each one of them. But each one of these billions of lines represents a particular form of quantum vibration of the phosphine molecule at very specific frequencies of life. But vibrations at specific intensities and frequencies is exactly what music is. So I recently collaborated with the composer David Ibbett to map the spectral behavior of phosphine to the audible range, effectively sonifying phosphine. So this is what phosphine looks like, but this is what phosphine sounds like, transforming the complex quantum behavior of the phosphine molecule into a solo cello piece. Recently, I was lucky enough to hear Minjing Chung perform this piece, and so I will post a link to the last rehearsal that we had, and you can hear the sound of the terrifying and mysterious phosphine molecule. So here are the takeaways. To be able to one day detect life, we'll definitely need bigger and better telescopes. And as you've heard with the Webb, we're getting really close. And within the next few decades, we'll be able to point these bigger and expensive telescopes at a potentially inhabited alien planet. And we'll be able to look at these planets' atmospheres. But today, we're not quite prepared to both detect and understand all the molecules on an alien planet. So my biggest concern is not that we'll fail to detect a habitable planet. My biggest concern is that we will point these telescopes directly at an inhabited planet and just not have the tools to know it. But by collaborating with people of all ages and fields, and by considering all the possible molecules that could form the context of an atmosphere, I aim to provide the tools to understand alien planets so that together, one day, we'll know life when we see it. Thank you.
Thank you so much. That was so interesting. And we have a bunch of questions rolling in. So folks, if you do have any more questions, you can put them in the Q&A if you're joining via Zoom, or you can put them in the comments on Facebook or YouTube. So one of the first questions we have is from Susanna, and she would like to know, could life on another planet exist very differently than ours, such as in another dimension, or does life on another planet have to take a three-dimensional form like we have?
So, interesting question. It is possible that alien life could evolve to really transcend what we think of as life as we know it. You know, they could become technological consciousness, for example. And so there are speculative forms of alien life that we may just not be able to detect. But if you think about life on Earth, we have had millions and millions and millions of species in our lives, in our history. And this is with the atmosphere looking really differently at the beginning of life than what it does now. And we've had a vaguely technologically advanced species, just the one, for a blink of an eye in our history. And so, although it's possible that some of the alien civilizations will be undetectable, most of them should still be detectable just because of the numbers. It's much easier to have life that is simple than life that is complex. And even if that life is complex, a lot of the signals that they have, for example, radio signals, are very bright, so we can detect those. And even if it's an alien civilization much more advanced than ours, one of the things we may find very easy to detect is the changes they have made to their solar system to try to, for example, mine planets or collect more of the sun's light. These are very easy to spot. And so there are a huge range of complexities that we can detect, but yes, we could always miss them.
It makes me think of, you know, when you think about like Andromeda Strain and even other sorts of sci-fi works, you know, a lot of the first contact with life are these tiny little molecules, you know, or these like tiny, you know, bacterium that we can't really understand yet, as opposed to, you know, people like us.
Of course, and I would love to meet aliens with whom I could like chat.
Right.
But the most likely thing is, you know, I'll find some alien mushrooms, but that would be so cool. You know, I will take any aliens at this point.
One of our other viewers, David, would like to know, are you only looking for carbon-based life like we have here on Earth?
Excellent question. So there's a huge variety of carbon-based life to look at. I specifically try to look for life not associated with oxygen. So the kind of hidden life we already have on Earth. But no, there are other forms of life that we can expect to find. For example, silicon-based life is possible, but it's very hard to expect the same level of complexity. The alien life we might find may be very strange, not carbon-based, or strange dimensions that they can access, but they still have to make use of the laws of physics, which we know are universal. And we also know the laws of chemistry are universal. So these might be really strange life forms, but they still have to make use of the periodic table that we have. And that's really reassuring that we're all working with the same rules. Now, we know the laws of physics are universal. We know the laws of chemistry are universal. We've been able to test them, but we don't know what are the universal laws of biology. And so that's work that I'm hoping this next generation will be able to fix. When we find alien life and we find more and more of it, maybe we'll establish these laws of biology. But the work we've done so far shows that depending on which biochemical choices you make at the beginning of your evolution, based on the planet you have and the resources you have, some choices, some biochemical choices, silicon-based chemistry could be one of them, have a cap on how complex you can get. So you can only maybe make grass level aliens if you choose a certain biochemistry. And if you choose a different biochemistry, you can make, giraffe level aliens. And if you make a different biochemical choice, maybe you can get to human level complexity. But there are caps depending on the choices you have to make as a life form. And so that's something we are exploring now, the chemical space of life. But as you can imagine, there's a lot of unknowns because we only have the Earth to work with.
Right. So, and we have a couple questions in a similar vein. Nicholas would like to know, do you expect RNA and DNA to be the basis of alien life like it is on Earth?
Not necessarily, though something that creates a similar function may be needed. For complexity to evolve, for evolution to happen, we may need a form of copying with changes. And once we're talking about copying with changes, we're now talking about evolution. So we're talking about something akin to, but we're certainly not trying to directly detect DNA like we know it. We're trying to detect just what aliens will release. Basically, very few things in the universe are completely efficient. Life will be in an environment because that has to happen. And they will take stuff from that environment like we do because that has to happen. They'll do stuff with it because that's what we do too. And then they won't use it all. Or they will produce waste product because nothing is completely efficient. And that we call signs of metabolism. Now, astrobiologists disagree on almost everything. No one agrees on a definition of life, for example.
Right.
But almost all of us agree that they have to metabolize. They have to take stuff in, do stuff with it, and release some stuff. So these, we call them metabolites. You can think of it as every time you burp or sweat or fart or breathe, all of these are you releasing into the atmosphere signs of life, signs of your metabolism. And so that's what I look for. I look for the signs of metabolism, the alien farts of the universe, because they got to do it.
Right.
They won't call them farts, but yeah, I know.
My alien farts of the universe.
I know. When I moved to this place, my neighbor apparently Googled me. And then next time we saw each other, he was like, this is a joke, right? Are you an alien fart expert? And I had to say, I wish that wasn't my identifier, but I technically, yes, I am.
I mean, embrace it at this point.
Yes. Not what I'd hoped to be known for when I was a child wanting to be an astronomer, but here we are.
So it seems also just like when we're searching for life, it's just so large and so vague because we don't really know what we're looking for. So what are other folks searching for life? We're not, I wouldn't imagine that everybody is searching for, the alien parts of the universe, but like, what are other things we're looking for as well at the same time? Because I imagine we have to be looking at a lot of different things in order to get our desired result.
Yes, so we're looking at those giant structures that show a civilization more advanced than ours interfering with their solar system. Mm-hmm. We're looking at radio signals, so signs of communication, like we have been sending out for about 100 years now. We're also looking for signs of life that we know here on Earth: water, carbon dioxide, methane, and their combinations. So those are the most common ways we look for life beyond Earth. And then there's people like me who are going just one small step further of looking for life not quite like ours, but that we know is possible because we have a few places on Earth hidden that produce it. So that's how far we've got. Some people are also taking it's called a more agnostic approach, where they're just looking for things that are weird. If you go to a planet, if you look at a planet and you see components of the atmosphere that we think, if we just left them be, they would react with one another and just change, but they haven't, then we can presume there's some disequilibrium. We can presume there is something awry, something strange, something that is interacting with the atmosphere in a nearly constant way. And those strange, seemingly chemically conflicting discoveries are another way that we look for life.
Great. We've got a bunch of things rolling in right now. Linda would like to know, how do you manage to simplify all of these complicated molecules and calculate everything and the number of the molecules inside of things? So I think really, like, how do you process all this data that you're receiving?
So the way I do it without crying is by telling myself that it's finite. There's only so many molecules you can make out of the periodic table. So I did calculate how long it would take me to do all of them, those 16,367 I mentioned. It will take me, at the rate I'm going, just a little over 62,000 years.
Oh, good.
So,
time.
So I do know I have a problem. And so that's part of the reason I put so much work into getting students and training scientists, because I need help. I cannot do this on my own. But the way we do it is with supercomputers. So we've only been able to do this quite recently. And it uses the Schrodinger equation. It uses quantum physics, things that we only learned about, about 100 years ago. And so it's all very new. But we can also use labs, laboratory work, to try to just measure the spectrum of these molecules. And so I have a lot of colleagues doing that work that have been doing it for decades. And so there is a small community within astrophysics that works on this, and we are working as fast as we can, but it's hard and we need more people.
Yes, we definitely need more people. That is true. We have some folks that like to know, Tanya would like to know, is it possible to have life without water?
Excellent question. That's one of the questions we ask about potential life on Venus, because Venus is horrible mostly everywhere, but the clouds, you could consider them quite nice if you didn't think about it too hard, because their temperature and pressure are lovely. It's like a mild summer day on the surface of the Earth.
Oh, beautiful.
Beautiful, except instead of having small amounts of sulfuric acid diluted in water, what they have is tiny amounts of water diluted in sulfuric acid. And so it is a horrible place to be because there is no water. So even if it was life that was very different from ours and didn't mine sulfuric acid, they still would need to not mine being completely dry, drier than the driest place on Earth. And water activity is really important for life, as far as we can tell. It's a really valuable thing to have chemistry happen. So we have that obstacle. Life on Venus would have to either be similar to ours and then have a really tragic existence, or be completely different from ours, embrace sulfuric acid, and not need so much water. And we have some simulations that show it is technically possible. We could use different solvents, is what we call it. So a bath of water is very good to make life in, but maybe we could have a bath of other things, a bath of sulfuric acid. Not fun for us, but maybe fun for our neighbors.
Right.
So we do simulate these things. It's just really hard to know because, as you can imagine, we're just making stuff up at some point, right, throwing some chemistry at it, but we still don't know how life happens, on Earth, the way we know about, the way we know it definitely happens. So it's very hard to predict new life forms.
Mm-hmm. And in a similar question, Nicholas would like to know, we hear a lot of talk about Europa and Enceladus as potential places for life. What do you think are the chances for life in those oceans?
Oh, I mean, wouldn't give you numbers on those chances, but that would be very cool. And that's certainly a place we look. The plumes of Enceladus would have these metabolites, these signs of life. So that's one of the places we're looking now. And in general, life, I think, will be inevitable. There's nothing that special about the Earth that would justify us being the only ones. That doesn't mean, fancy green aliens are possible, but some form of life, I think, is inevitable. And a lot of astronomers do agree with that. But whether it's common is much harder to know.
Mm.
One of the amazing things about discovering life in the solar system, where there are no environments like the Earth. So any life we find would have to be able to exist in completely different environments, like the subterranean oceans of Enceladus or the clouds of Venus. But that would mean that if life can happen in places as different as Earth and the subterranean oceans and the clouds of Venus, then it must not just be inevitable, it must be extremely common. And every planetary system in the galaxy probably has some. So it would be really wonderful to find life in the solar system because of what it would mean for life elsewhere in the galaxy.
Speaking of elsewhere in the galaxy, we have a question about Webb. And if you know what % of time Webb will be spent looking for signs of alien life.
Quite a bit. I don't know the exact number, but I know several observation proposals that are looking at planetary atmospheres have already been selected. Very few observations are looking exactly for signs of life. They're just looking at planet atmospheres, and then we interpret that data and try to explain what we see. You don't want to be looking too hard for something very specific. Otherwise, you might find it, but it might not be real. So you want to keep your kind of scientific integrity by just looking at an atmosphere and then just trying to explain it. So we have a lot of planets in our galactic neighborhood that we will be able to look at their atmosphere and see their rainbows. But I should point out that although the Webb telescope is the most complex, most powerful telescope we've ever put in space, so we will be getting better data about these alien planets than we will ever have been possible. It's unlikely we'll be able to get the full description of the molecules in an atmosphere. We may be able to see a few molecules, and if some of them shouldn't be there, that'll be really interesting. If we find oxygen and methane together, that will be very exciting. But we may need a future dedicated mission, which we do have planned for the next few decades, just in time for the students in this audience to become the experts. And those missions will be able to follow up on the observations that Webb made to see, okay, if there's oxygen and methane there, that's weird. Let's see what's the rest of the chemical context. And hopefully by then, in 2 decades, I'll be able to have created a toolkit with all those molecules that we're missing. And I can contribute to that. But yes, it will be a really crucial and very important step, the work that Webb will do to find alien life.
Are there so we've talked a lot about Venus and looking at the phosphine on Venus, and we talked about Enceladus and Europa. Are there any other planets that are kind of on the short list that we're really looking a bit more closely at?
Yes, Titan is a wonderful moon that has a thick, dense atmosphere that is so dense that if we could survive it and put some wings on ourselves, we could fly. Humans could fly. So it's a really dense atmosphere, and it has liquid. It's just liquid methane oceans. But we have some missions already planned and kind of paid for on their way, like Dragonfly, and they will be able to tell us much more about what's happening on Titan. But Titan is very promising as a place to try and find life.
Great. So
the moons of big planets are often, even if a solar system doesn't have planets in the right place for life, it can easily have planets like Jupiter and Saturn that the moons could have life, like Titan or Enceladus.
Yeah, is there something about, because when you think about our moon, we could never have life there, but what is it about the moons of those large planets that make them, a potential place for life?
Is that they have an atmosphere. So our
Mm.
moon is very cool, but it's completely stripped bare. It doesn't have an atmosphere, but other places do. And even if they don't have an atmosphere, in the case of Enceladus, well, it has a tiny, tiny atmosphere. It has liquid underneath its ice crust. So basically, you need something that isn't a solid.
Mhm.
You need some protection. So you need something above a liquid, or you need something above a solid, like a gas that can protect you. And so Mars has a tiny atmosphere. So it's very hard for Mars to shelter any life that may show up on its surface or even underneath. Enceladus doesn't have much of an atmosphere, but it has solid ice sheltering the liquid underneath. And Titan has a thick atmosphere protecting its surface, like we have an atmosphere protecting the surface. And Venus has an overprotective atmosphere protecting the surface. So yes, you need some shelter.
Great. So for our young astronomers out there who are going to be picking up the mantle in a few years, can you tell us a little bit about your journey to get where you are today? I mean, were you always interested in astronomy? What were the steps you took to get to where you are?
So I was interested in astronomy from a young age. My parents were both scientists, and they showed me an eclipse when I was 12, and they showed me how everything was going to happen. They told me the exact timings of everything, and I just thought it was so strange that they just thought they knew exactly at which time stuff was going to happen in the sky. And then they were right, to the minute. And it blew my little mind that they just knew this. It just felt like magic. And they explained to me it was a job, to be an astronomer, to predict the skies to the minute, to the second, really. And it was a thing you could do and get paid for. And that was me. I was sold at 12. And so I tried to do science subjects in middle school and high school. I try to call up local planetariums and say, I'll answer your phones, I'll work for free, and things like that. And then I did a physics degree and an astrophysics master's at Edinburgh, and applied for a PhD. And so I very much tried to do the path, the academic path, as best as I could. But it was interesting to realize that I initially thought I'll just study planets, to try find life, and realizing around the time I finished college that really the quantum behavior of molecules, which was something I'd ignored completely. I didn't do chemistry in high school. I had no idea how molecules worked. I almost failed quantum physics in college, so I really didn't know anything about chemistry or quantum, never mind quantum chemistry. But it was around the time where I was trying to really do research that I realized that that was all missing. And I became really invested in how cool it is that looking at the smallest thing, the quantum behavior of molecules can be the answer to like the biggest questions, like, is there life on that planet? And that kind of scale gap really, really seemed the coolest thing to work on. And that's been me ever since.
That's so great. Do you have any advice for our future astrophysicists out there, future astro or quantum astrochemists?
Well, this is one path. You can be really focused, and I definitely don't want to make anyone feel bad for being focused, but you should know that there have been times in my career, many times, where things weren't going well. My research wasn't going well. Looking for jobs wasn't going well. And I thought, I was so focused. I never had a plan B. And that really was tough. I felt like too much of my identity had been attached to this career. And now that I might not make it, I felt really lost. And I thought that was really not a good choice, that if I had been a bit more open to other fields, that I would have struggled less. And that might be true. And I certainly know it can be true because most of my colleagues had really strange paths. One of my best collaborators is a biologist who went into pharmacy first and then realized that the chemistry he was doing for pharmaceuticals could easily be used to try and understand hypothetical forms of life. And so he joined the team. We have people who just really didn't know anything about space, but were very good with computers. We have my colleague, David Ibbett, who's just a musician, a wonderful musician, and composer, and learned enough quantum chemistry and astronomy to be able to sound it out. And so it is, particularly with something like astrobiology, it takes a village. You can't just be an astronomer, you can't just be an engineer, you can't be a biologist, you can't be a philosopher, you need a bit of everything. And so my advice for people who want to do this sort of work is find the thing you like, and it will probably be useful for the search for life beyond Earth. Don't worry too much about the path you take.
Awesome. That's great advice. Thank you so much for joining us this afternoon. Really appreciate you and your time in answering all of our questions. So for the folks at home, thank you also for joining us. If you want to learn more about exoplanets and Clara's work, before we leave, I want to encourage you to check out the NOVA Exoplanet Lab. So during this lab, you're part of NOVA's galactic resettlement team, and you have received a distress call from aliens in desperate need of a new home. So to help, you'll have to master the same techniques that scientists use to find and characterize exoplanets. So before we leave, I want to take a quick peek at the trailer, which you can see Clara in. So let me just quickly share my screen, and we're going to take a look.
Gina, I don't know if you're sharing sound.
Oh, I can do that. I will share my sound. There we go. That's better.
Welcome to our NOVA Space Center, ground headquarters for our Space Exploration Division.
Our mission is to explore the cosmos, discover planets beyond our own, and act as stewards of the Earth.
Let me be the first to congratulate you on your acceptance to the NOVANAUT program.
Based upon your sense of adventure and your can-do attitude, we've assigned you to one of our most important programs, the Galactic Resettlement Team.
You'll be the lead scientist, working to discover new homeworlds for displaced extraterrestrials.
Aliens. They need new homes, and you're gonna find them.
A couple of days ago, our lunar outpost received a distress signal.
You need to go investigate.
Ready?
So that's just a sneak peek of the lab, but during the entire lab, you will be able to look at atmospheres, you will look at radial velocity, you will look at transit data, and make a bigger picture of how you can help your alien friends find a new home. So thank you also, Clara, for participating in that with us. So if you'd like to learn a bit more about her work, you can play the lab as well. And thank you for joining us today. Thank you for answering all of our questions. And thank you to our viewers for being here and asking our questions, because without you, this conversation would not have been possible. So if you'd like to learn more about Nova Universe Revealed, which is one of the reasons we are all here today, all 5 episodes are available to stream right now on NOVA's website, pbs.org/NOVA. If you want more information about exoplanets, about space, Universe Revealed, you can follow NOVA Education for updates on new content and virtual field trips. So we want to wish you all a safe and healthy rest of your week, and we will see you at the next one. Thank you again for joining us.